We have our heart chambers all ready to go. We've got our valve system. We looked at the cardiac cycle that we went through, the systole, the diastole, all 5 of those stages, which really includes that 5th stage, atrial systole or atrial contraction. So now we want to look at the electrical coordination of the cardiac cycle. Remember we said when we talked about cardiac muscle is rhythmic and spontaneous. It does not need or require any innervation from the central nervous system to beat, and to beat regularly. So we're going to see that the myocardium of the heart is going to be instructed to beat by a group of cells that sit in the right ventricle called the sinoatrial node. And because our cardiac muscle cells are linked via gap junctions, when the cells adjacent to the sinoatrial node depolarize, all of the cardiac muscle cells will depolarize until we get to the annulus fibrosus. And remember, that's going to be a connective tissue layer, so it insulates that electrical signal. So when we start the conduction, the signal to contract, all atrial cells are instructed directly from the sinoatrial node. Then we're going to see we relay that signal through the annulus fibrosus to get it to the ventricle. Because the annulus is not just an insulator, it's also going to be a sturdy layer upon which the valves and the septa of the heart attach. So sinoatrial node, SA node. How do you think they came up with this name? Atrial is easy. But sinus, I thought that was in your nose. A sinus is sort of an open cavity, but you got the right atrium, and an atrium is sort of an open area. But where the sinus comes from is from embryonic development. Because in an early stage of your development, you had a 2-chambered heart. A single atrium, a single ventricle, an atrioventricular canal, and all of the blood coming back from the body, primarily in the cardinal veins, emptied into a chamber, if I can loosely refer to it as a chamber, that immediately led to the single atrium. That chamber was called the sinus venosus. Guess what activity resided in the embryonic sinus venosus? The pacemaker activity. And as we're going to look through development, your right atrium actually incorporated that sinus venosus tissue into the smooth portion of your right atrium, and it brought that sinoatrial node activity with it, the pacemaker activity. So that's why it's referred to as sinoatrial node, from the sinus venosus now in the atrium, SA node. And since this is the pacemaker activity, when you have a normal rhythm conferred by the SA node, what kind of rhythm do they call normal rhythm in a clinical setting? Sinus rhythm. Again, sinus rhythm has nothing to do with your nose and everything to do with the SA pacemaker that's present in your right atrial tissue. Now we're going to sort of back up, if you will, and we're going to be looking at action potentials, depolarizations and repolarizations and hyperpolarizations. And the SA node is going to spontaneously depolarize when the membrane potential becomes hyperpolarized. It's just going to be an automatic trigger. That's why it keeps going, like the metronome, if you've ever endured that punishment in any kind of musical lesson. So we're going to start when our electrical potential of our pacemaker cells, this is not cardiac muscle yet, this is pacemaker cells, when we're at a hyperpolarized potential. And minus 60 is going to be about that level for our pacemaker cells. Now, this is immediately at the end of our previous action potential. Do you remember the after hyperpolarization in neurons? Well, this is the after hyper. After we repolarize and it goes down, that's the after hyper. That's where we're starting here. And so when we're in this hyperpolarized period, there are going to be channels that are called HCN channels. The HCN stands for hyperpolarized cyclic nucleotide channels, cyclic nucleotide being like cyclic AMP. And when these channels open at that hyperpolarized membrane potential, this is going to lead to ion channels that allow a lot of sodium to rush in and a little bit of potassium to go out. Sodium coming in, what does that sound like from neurons? Yeah, that's the initiation of an action potential. And so what's happening when sodium comes in, you begin to depolarize as you're getting more positive. And this is referred to as diastolic depolarization. Why do you think we call it diastolic depolarization? What does diastole mean? Relax. So we're beginning to depolarize while the heart is in a relaxed state. Here we have a graph. We're showing the hyperpolarized periods for 3 action potentials that are happening in sequence. And when we get in this hyperpolarized part, the green portion of the line are when the HCN channels activate. Sodium comes in, and now you can see that depolarization becoming more positive. Now, as we become more positive, we get to the next step. Diastolic depolarization, that threshold. Voltage-gated, what is that? Calcium channels open. Calcium channels open, that's going to lead to a contraction. But what we're also going to see is these calcium channels cause a depolarization event, going positive upwards of positive 30 millivolts. This is where it differs from what we saw with neurons. Now, while we don't have nervous system innervation to beat, we do have control of the rate and strength of the contraction from our autonomic nervous system. So epinephrine and norepinephrine, they're going to stimulate what receptors? Beta 1s. That's going to produce our cyclic nucleotide, cyclic AMP. And that's going to keep our HCN channels open, and it's going to increase the rate of depolarization. So if you look at that slope of that red, the HCN channels, when epinephrine and norepinephrine hit, that's going to increase the slope, the activity of those HCN channels. It's going to move those action potentials closer together. Your heart's going to beat faster. And opposite acetylcholine, it's going to open potassium channels that decreases the polarization rate, lowers the slope of our HCN activation, and moves those action potentials further apart, which slows the rate. So here we see our HCNs. There's our voltage-gated calcium channels. That's our depolarization stroke going up. Once we get into positive 30, repolarization. And here's our old friend, the voltage-gated potassium channels, and it's going to be the potassium channels then that lead to the downward repolarization. We're going to have our normal after hyperpolarization, but once we get here, we don't need sodium-potassium pumps like we saw in neurons, because when we get hyperpolarized, HCN channels activate open. We have our HCN slope. Pacemaker potential is what they refer to this in red, and then we get our diastolic depolarization, and we do it all over again and again and again your entire life. That's the electrical activity that occurs spontaneously and rhythmically from our sinoatrial node. And the cells of the sinoatrial node are specialized. They have gap junctions. They're connected to our myocardial cells in the atrium. And when that depolarization flows through, those ions flow through and depolarize those atrial myocardial cells, they go through a similar yet different electrical potential cycle. And so these are your myocardial electrical potentials. We start with depolarization. SA node cells use voltage-gated calcium channels. Here we're going to use sodium channels, voltage-gated sodium channels, just like we saw in our neurons. But we're going to see a little difference in our repolarization. Repolarization is going to happen in 2 stages. So we're going to have a plateau stage that's going to happen. Now, normally we have sodium voltage-gated channels depolarize, voltage-gated potassium channels repolarize. It's a spike. So what I want you to understand that for repolarization, we are going to open voltage-gated potassium channels. You are going to start to come down. But then, quickly following those voltage-gated potassium channels, we also open voltage-gated calcium channels. Now, do you remember where calcium is highest concentration? The way I remember this, think of the terminal bouton for our axon. Calcium had to move in which direction it leads to? Into. So calcium is highest outside of the cell. So here potassium positive is moving out to decrease the potential. But then we have calcium channels, calcium flooding back in. What is that going to do to our membrane potential if you've got positives and negatives going in and out? It's going to be unchanged. And that's going to be the plateau that we see. But these calcium channels are going to be only open for about 200 to 300 milliseconds. And then in the final stages, the calcium channels close. The potassium channels are still open, and that's going to finish our repolarization. I know that's a little complex, but hopefully in this illustration, we can see it a little bit better. Now, this is a little misleading because the potassium out that you see on the right looks like it's happening here. But understand this potassium out starts at the very top. Potassium out is happening the entire time. The calcium in only happens where you see that shoulder. Does that make sense? This little spike downward that you see at the very top, that's due to potassium channels only. The very rapid completion of our downward spike, that's potassium channels only. But this flat shoulder, this flat plateau, is due to the potassium channels continuing to be open, but additional calcium channels opening. And that opening of those channels in this plateau allows for a longer, more sustained contraction. Because the heart's going to try to squeeze the right amount of blood out with every beat, with every contraction. So our SA node cells set the pace. Our myocardial cells, being all connected, respond to that electrical signal and they contract. But that's only our atrial cells, because the electrical signal cannot spontaneously pass through the annulus fibrosus. So we have to conduct the signal from the atrium through the annulus fibrosus into the ventricles. And we used specialized myocardial cells to do this. And so the first specialization we're going to see is in the atrioventricular region. We have a cluster of these specialized cells that are called AV node cells. They're going to be connected to the myocardial cells in the atrium. So the SA node, the pacemaker, depolarizes. Ions pass through the gap junctions, cause depolarization of the myocardial cells. They're connected via gap junctions to our AV node. It depolarizes. And our AV node then is going to send that signal through a bundle of fibers. Think of them like a fiber optic cable. And this cable is called the bundle of His, or the AV bundle. This is going to go through the annulus fibrosus. It's going to go down through the interventricular septum, And at the base of the ventricle, the apex, that point like you draw at Valentine's Day, those fibers are going to spread out. And the individual fibers are referred to as Purkinje fibers. The AV bundle is made up of a bunch of these Purkinje fibers. But these Purkinje fibers spread out and they release the action potential at the base of the heart and along the walls of the ventricles. So the cells that depolarize first are the cells at the base of the heart. So the heart contracts from bottom up because that's where we're wanting to move the blood, up and out. So SA node fires. That signal passes through the myocardial cells to the AV node. It depolarizes, sends the signal through the Purkinje cells of the AV bundle. The Purkinje cells release those ions into the myocardial cells in the base of the heart. Those cells undergo depolarization and contract. But there's one additional thing that happens, and it's conferred by the AV node. Not only does the AV node pick up and transfer the signal, but the AV node also pauses. It picks up the signal and it pauses for 1/10 of a second before it relays that signal to the ventricles. Do you understand the significance of that? Think of our cardiac cycle. 3/10 of a second, ventricular systole, ventricular contraction. 5/10 of a second, diastole, ventricular relaxation. What happens 1/10 of a second before the ventricles contract? What's step 5? Atrial systole. The atria contracts. 1/10 of a second later, the ventricles contract. Because remember, the atrium's squeezing that last 20% of blood into the ventricles, that end diastolic volume, so that now we can force the blood out. That 1/10 of a second delay is conferred by the atrioventricular node. So it's not just some trivial thing, that pause. That's one of the more important things that happens in the AV node. So in our cutaway of the heart, we see the SA node in our right atrial wall. We see the AV node down at the base of the atrium. Here's our bundle of His diving through our interventricular septum that separates right and left ventricle. Then the fibers are released at the base, and this is where the signal begins as the heart contracts in the upward direction. That's our electrical conduction of our action potentials leading to our cardiac cycle, leading to the heartbeat. Now, what's really cool, even though the heart, you feel like it's deep inside the body, it's at your core, you can pick up these electrical signals on the surface of your skin. And this was done decades and decades ago, first in Germany, and that's the reason we call it an EKG, because in Germany, cardio starts with a K. And we've left that convention because EKG, when you're writing out all these orders, it's more difficult to confuse between EEG, electroencephalogram, and an ECG, echocardiogram. So we've just left the convention of the EKG. So as these electrical potentials occur inside your cardiac tissues, you can detect them on the skin with various electrodes. And these waveforms that you're going to see can give you quite a bit of diagnostic value in the look at the health of the heart. And so here in our illustration, very early on, you had these electrodes on your ankle and your wrists. Well, they've refined them now to put them on your thorax, and you can either have 3 lead, 4 lead, 5 lead EKGs or more. And the electrical signals that are picked up are the EKG and look similar to the waves that you see in a lot of commercials, a lot of business cards, a lot of home health advertisements have the EKG. You see that, you recognize, oh, that's a heartbeat. the electrical activity leading to the beat. And when we look at an EKG in normal circumstances, and I believe this is a 3-lead EKG. With more leads, these look different. But our normal 3-lead EKG, you're going to see a couple of waves. The waves are defined by certain points such that the first small wave is called the P wave. Then points Q, R, and S, that's referred to as the QRS complex. And then we have the final wave that is the T wave. And we can correlate this to the electrical activity that's occurring in our myocardial cells, such that the first wave, the P, that occurs when you have atrial depolarization. Remember, we said there's not a lot of muscle in the atria, because are they really doing a lot of work? They're only pumping 20% of the blood that the ventricles do. Plus, they're moving it in the direction of gravity. They're just moving it straight down. Whereas the ventricles, especially the left ventricle, where does the left ventricle have to be strong enough to pump blood to? The left ventricle has to be strong enough to pump blood not only to the big toe, but also back to the heart from the big toe against gravity. So the left side of the heart is going to do much more work than the right, and both ventricles are going to do much more work than the atria. So that's why the P wave is rather small. The QRS complex, this is the biggest because it is depolarization of the ventricular myocardial cells. A lot more of them. And then the final small wave, the T wave, this is repolarization of the ventricles. Now understand the atrial repolarization is also going on, but it's so small compared to what's happening in the ventricle, it's masked. You don't see it. Now I also want you to understand our refractory periods. Remember we had those with our neurons? Well, our absolute refractory period starts at point Q and it ends at the apex of the T wave. From the apex of the T wave to the end of the T wave, that's going to be our relative refractory period. That's important because the faster your heart rate goes, the closer these waves get together to the point that, okay, you're getting into that relative refractory period. You can't go any faster because you can't establish a second action potential any sooner because of the relative and then the refractory, the absolute refractory periods. Now, this is a neat little animation. And I hope it works on the video. But here it correlates the electrical activity with your EKG and the waveforms. So when we start, there's our sinoatrial node, depolarization of the atria. There's our AV node and the pause. The signal's sent to the ventricles, they depolarize. And now basically repolarization of the whole thing, but especially the ventricles. Now again, understand we're looking at electrical activity, not the mechanical contraction, but you can correlate them fairly closely together. So clinically speaking, we don't just look at the waves, but we also look at possibly the regions including or the regions between. If you're looking at the region between waves, that's called a segment. If you're looking at portions that include a wave, those could be referred to as an interval. So you see the PR interval from the beginning of the P all the way to the Q. We have the QT interval. This includes the entirety of the QRS as well as the entirety of the T. You get an idea of the segments versus intervals. And it's many of these that are going to be clinically significant. So the PR interval. We know it's going to range anywhere from 120 to 200 milliseconds. If you change the timing of these, that's indicative that you may have some pathology going on with your cardiac tissue. Our QT interval we saw includes both the QRS and the T waves. The PQ segment, this is going to be important because that's the 1/10 of a second in which the AV node is conducting and pausing the signal. If that number changes, that could lead you to deduce that there's something wrong with the AV node. But ST, this is probably the one that is most significant because if you have a change in the ST segment from the end of the QRS to the beginning of the T wave, if there's some changes that happen there, that's indicative of a myocardial infarct or a heart attack. So let's examine some EKGs. And when you look at a normal EKG, again, which we refer to as sinus rhythm conferred by the SA node, we can see the repeating cycle of our heartbeat and the electrical activity. So what would this wave be? Let me point one out. What would that wave be? That's the P wave. What is that? P wave. That was tricky, wasn't it? What's that? T. This is the N. So you're looking at these units. These are the repeating units. So P, T, the QRS are fairly easy to see. So that's our normal sinus rhythm. Now, don't get overwhelmed by this one. This is one of my favorite slides because of all the information that is packed into this slide. So when you look at this, not only does it show you our cardiac cycle stages, there's our IVC, there's our IVR, ejection, rapid filling, atrial systole. You see that along the top. We can also see our waves down toward the bottom, the P wave, QRS, and T. Here we have our heart sounds, S1, AV valves closing. S2, our semilunar valves closing. And you can also see these demarcated in the changes in our ventricular pressure and ventricular volume. So this one graphic compresses together a ton of information. And just by learning this graph, it will serve you well in the future for anything you have to know about the cardiac cycle. I think you're not surprised that not everyone has a normal heartbeat. Cardiologists would be out of business if we did. So normally we have about 72, 75 beats a minute at rest, but there's a condition called bradycardia where your heart rate is slower than 60 beats per minute. Now, if someone experiences bradycardia, should they go to the doctor immediately? Why not? Well, how long they've had it. Some people may experience bradycardia maybe for 6, 7, 8 hours a day. In fact, most of all of us do. When you're asleep, your heart slows down. So you have physiological bradycardia versus a pathological or a clinical bradycardia. If I were to run up and down the stairs outside and my heart rate didn't get above 60 beats a minute, something's wrong. Because I can just look at a flight of stairs and my heart starts getting fast. So you see the difference. Pathological bradycardia versus physiological. And this is what bradycardia looks like. Is there anything wrong with the P waves? Anything wrong with the T's? QRS look okay? Yeah. You just have fewer of these cycles. Again, rest and digest. Acetylcholine facilitates this spreading out of our cardiac cycles and slowing of our heart rate. Likewise, tachycardia, anything faster than 100. If you're doing something really strenuous, yeah, it's going to get faster. Where the clinical situations come in is if you have the atria or the ventricle undergoing tachycardia when you're not exerting yourself. And they can do this independently of your SA node or of each other if there is what is called ectopic pacemaker activity, extra pacemaker activity. If some of your myocardial cells are rebels and they want to dance to the beat of their own drum and they set their own pace, whenever they depolarize, everybody will. Atrial tachycardia, is that going to be a big, huge clinical deal if the atria is beating really, really fast, as long as the ventricle's not? No, because the atria is only doing 20% of the work. Remember, rapid filling is just 80% of the blood that's in the atria getting sucked down. Atrial tachycardia, not a big deal. Ventricular tachycardia, this is a huge deal because ventricular tachycardia, or VTAC, can lead to another condition that's called fibrillation. So if you're in VTAC, you've got problems and you need immediate intervention. So here we have sinus rhythm, sinus tachycardia. Sinus tachycardia means normal rhythm, just faster. Notice what's happening to our P's and our T's. Man, the T wave isn't even finishing before the P wave starts. Remember, we're in that relative refractory period that allows us to start another cycle, but we're not going to get much faster than this. Because then the P's moving into that absolute refractory period and we simply can't go faster. This is somebody having a bad day. If you see this on an EKG, you better hit the code blue button. That's ventricular tachycardia. Atrial tachycardia is you're going to see a bunch of P waves and only one QRS. So VTAC, not good. Now, other things that can happen, we can have flutter, coordinated but extremely rapid, 200 to 300 beats a minute. We're getting into hummingbird wing speed here. And I think you can see how this would be a problem. But the biggest problem of both of these is going to be the second one, the fibrillation. Because fibrillation is disorganized. And because it's disorganized, you see these last two words here? No pumping of the blood. Fibrillation is as if the blood, your heart isn't working at all. It's quivering. It's not moving the blood. Now again, if it happens in the atrium, it's kind of no big deal. Because again, the atrium's not doing that much work. And so here is a atrial flutter. And you can see all of those P waves. It's almost difficult to find the T in with all of those. Look at the atrial fibrillation. Man, the atria is just quivering. AFib. You don't really want to leave someone in AFib all the time. Because as the atria is just quivering, you're going to be agitating the blood, including agitating the platelets and clotting factors. So if someone has AFib, they're probably going to be on some sort of beta blocker to try to stabilize the rhythm so that you can't go that fast. Remember, fast is sympathetic, beta blocker, antihypertensive. But you're also going to put this person on Coumadin. You want their blood not to be as coagulative, if I can invent a word there. You want that blood to be thinner because of all the disruption that's happening. Now, this is the most clinically relevant of our arrhythmias, ventricular fibrillation. Now, again, typically we're going to start out in VTAC, ventricular tachycardia, and then we'll move into fibrillation. But this is also referred to as a circus rhythm. It is so disorganized. But with fibrillation, if you don't get the heart out of this disorganized state where it's not pumping blood, death's going to occur in just a few minutes. So if someone is in fibrillation, what do you, as a first responder, what do you do? CPR. Okay. We're wanting to pump the blood, so you got CPR. And in fact, the very first thing you do is you call 911. Then you start CPR. But if you are in this building, if you are in this room right now, I drop down and I go into fibrillation. What is someone better be going to get? It's right outside on the wall out here. The kit, which is AED, not the organization, AED, automatic, electronic, what's the D stand for? Defibrillator. What does that word actually mean? If you defibrillate, what are you doing? Removing or stopping the fibrillation. And the way this works, think about our SA node. How does our SA node understand when to start another beat? When the electrical potential is hyperpolarized. Remember that voltage? So, when you defibrillate a patient whose heart is just all disorganized, when you hit it with all of that voltage, you are putting every myocardial cell into an absolute refractory period at the same time, including the SA node cells, in the hopes that when they exit that refractory period, the SA node will start back with a normal rhythm. And whatever ectopic signal that was causing the fibrillation, hopefully that would have been reset or eliminated. That's the hopes. That's the plan. That's why you do the defibrillation. So if all of our rhythms that we've seen, all of our EKGs, the VTAC was bad. But remember, VTAC leads to this. And notice there's really not much there. And from VFib, ventricular fibrillation, asystole is next. And remember, A in front of a word, none. So what does asystole literally mean? No contraction. That's the flat line. So VTAC, VFib, asystole, game over.
And then you should progress from one to the other.
Yeah. Now, a lot of times you're going to see these situations happen because of what is referred to as ischemic heart disease. When you cut off the oxygen supply, which means you have restricted the blood supply, that cardiac muscle is not going to function well. It's aerobic. It is not anaerobic. And a lot of times this is going to happen because we develop what is referred to as a thrombus or a clot, a blockage. We're going to have this plaque of cholesterol-rich and fatty material that builds up inside of our blood vessels. And we refer to this as atherosclerosis. Arteriosclerosis being a subcategory of atherosclerosis, and these plaques are going to be atheromas. So if you've ever looked in some old piping in an older home, especially sewage piping that's got all this gunk built up on the inside of the pipe, you really restrict the diameter of that vessel. Well, what's going to be happening to the pressure of the fluid that's trying to get through that smaller opening? The pressure is much higher. Your heart trying to pump all this blood through the smaller diameter, the heart's going to have to work harder. And so a lot of this has to do with your cholesterol, and we're going to talk about a couple of different types of what are referred to as lipoproteins, the good cholesterol and the bad cholesterol, because some cholesterol is actually going to help you. And in this illustration, you can see from the initial beginning, the deposition, you can see how much you are restricting the luminal diameter of that vessel. Until we get to the point here at the very bottom where we have complicated lesion. It's complicated because you've packed so much fatty material under the endothelium. Remember, our endothelium prevents blood clots because it's intact, it's got the CD39s, it's producing other substances. But what happens when you pack so much stuff up under there? The endothelium ruptures. Now your blood is exposed to connective tissue, von Willebrand's factor. You start making a clot, a platelet plug. Well, if that's happening at the peak here, and you've got this blood flowing under higher pressure, that clot, that thrombus, you're going to break it off and it's going to go lodge somewhere else. And that could be disastrous. Heart attack, stroke, emboli. So this is the real danger, not only the hypertension that happens, but the clots that can form if it's left untreated. And if you're restricting the blood in a coronary artery, depending on how much that blockage is and which artery, I mean, it could be just a matter of seconds from when you completely block that off to when you're gone. Left anterior descending coronary artery. It's also called the widowmaker. If you block that one, game over. So let's look at these cholesterols we refer to as lipoproteins. And there are many of them listed, 5 groups of these, including the chylomicrons, which are used to transport the fats that you absorb out of your digestive system. But these lipoproteins, these are those packages of material that are largely going to transport substances that are water insoluble. Remember when we talked about bilirubin? We talked about transporting iron. Well, in this case, we're going to be transporting fats, triglycerides, cholesterols. We're going to package them inside a vesicle that's surrounded by phospholipids. The fatty acid chains are pointing toward the interior, and the charged heads are on the outside. So we have a water-soluble package whose contents are water-insoluble. And this entire unit is called a lipoprotein. Now, we're also going to have proteins that are embedded into our phospholipid layer. They're going to act as zip codes or addresses to know what to do, where do we send these things. But with our lipoproteins, we have some that are the good cholesterol, high-density lipoproteins. We distinguish these by and large by those proteins, and the high-density lipoprotein is going to have a protein on its surface that's called ApoA1. So HDLs take the cholesterol that's in your blood or removes the cholesterol from your blood vessels and organs, brings it back to the liver where it can be broken down and processed. She said how that's the good cholesterol, the removing it from where it could do damage. I love this little picture because H can stand for halo. Helps you remember H halo, that's good. In contrast to the opposite, it's good. And when we look at the bad cholesterol, LDL is bad. The L could stand for Lucifer there. You can see the little devil horns. Bad. LDL just does the opposite. It takes that cholesterol and deposits it in the tissues. And we distinguish the LDL from the HDL because the protein here is ApoB100. You see how the address changed? Looks the same, phospholipids, cholesterol, triglycerides on the inside, but the address, the protein, the zip codes are different. So that helps us define the function of these lipoproteins and distinguishes the good from the bad. Now, regardless of your genetics, diet and exercise is going to be important. But if you have bad genetics, it's going to be even more important for you that you watch the intake of fats and you get plenty of exercise. Now, we call that whole package a lipoprotein. Here we see those protein zip codes, ApoA1, ApoB100. Those proteins are referred to as apolipoproteins. I know it gets a little confusing, the terminology sounding very similar. But the apolipoproteins are basically ligands that are going to bind to receptors in your tissues and blood vessels. So ApoA1 is more likely to bind a receptor that you find on your hepatocytes, your liver cells. Whereas ApoB100, it's going to be more predominant in your tissues and in your blood vessels. You see how those are going to help anchor these in the right place so that the cells can process them accordingly. So ischemic heart disease, sort of back to that. If we have too much LDL and we've deposited that material in our blood vessels, that's going to restrict blood flow. And in this illustration, you can see these blue lines. That's where we've got low oxygen because we've blocked off this coronary artery. It's on the right side. Right side's not great, but it's better than the left because the right side doesn't do quite as much work. But if you start to destroy myocardial muscle, if it starts to die, you're going to have pain. And it's substernal pain. Some people are going to think it's heartburn. I forget which celebrity last sort of went through this, but she's like, I thought I just had heartburn, so I didn't go to the doctor until it got really bad and went and found out I'd been having heart attacks. But more often than not, what's going to get your attention is your shortness of breath, the intense pain, but that pain is going to radiate down your left arm. And that's called referred pain. A lot of times you'll see people, if they're having a heart attack, like in the movies or whatever, they'll grab their arm. They don't just grab their chest, they grab their arm. That's because of this referred pain from the location and your nervous system and those pain receptors. But if you're having any kind of pain in your chest, any kind of pain in your arm, get to the ER. And I promise you, have you ever had to wait in the ER for hours and hours? You ever had to do that? Promise you, you go into an ER and you tell them you're having chest pain and it's hurting in your left arm and shoulder, you will get a bed immediately. You will not wait because they know it's just that serious. Now with the myocardial infarct, we already said if you have a change in that ST segment, that indicates that you have had a heart attack and you've got some tissue damage in the heart. But you can also do blood testing that's building a case for a heart attack. If you see creatine phosphate or creatine phosphokinase, if you see that in the bloodstream, why would you think that's odd? Where do you normally see creatine phosphokinase? It's that backup system in your muscle cells. You shouldn't see it in your blood. If it's in your blood, there's been some muscle that's died and broken down and released it into your bloodstream. And if you're in there because you got chest pain, well, the muscle we're probably talking about is the heart. Lactate dehydrogenase, again, a muscle-specific enzyme. Troponin. Why in the world would you have troponin in your blood if muscle cells have broken down? So again, there's a real technical tenet in science. If it walks like a duck, talks like a duck, poops like a duck, it's probably a duck. Well, if you have all these muscle markers in the bloodstream, you have a change in the ST segment, and you're experiencing chest pain, that's what brought you to the ER, well, you can put money on the fact that you have had a myocardial incident. So this is an example of an ST segment depression. Do you see how after our QRS, our potential stays low? It doesn't come back up to our baseline and move over to the T wave. ST depression. Look at that shoulder on our elevation. So a depression or elevation, any change in ST segment, your first thought is a heart attack.